Hey guys, this is Sakshi back and I welcome you all to my editing platform, Way to Learn. So here we are going to solve some of the problems from PYQs of thermodynamics and let us see what is the first question. Before that, I have already solved around 6 questions from June 2011 and December 2011. Now let us see the 7th question, which is from June 2012. Okay, so here consider again a black body radiation contained in a cavity whose walls are at temperature T. The radiation is in equilibrium with the walls of the cavity if the temperature of the walls is increased to 2T. So remember, the walls are at temperature T first and then the temperature is increased to 2T. And again the radiation is allowed to come to equilibrium at new temperature 2T. Okay, so now the entropy of the radiation increases by a factor. So at first what was the entropy and at the second time what was the entropy. So we'll have to find how has our entropy increased or decreased, whatever it is. So first, for black body radiation, you'll have to remember the U internal energy is sigma T power 4. Okay, so this is a basic thing. You'll have to remember this sigma T power 4. Okay, so now we know that TQ is equal to TDS or DU is equal to TDS. So we have U here, so DS will be DU by T because we have to find our entropy for two different temperatures. So for first temperature T, we can use du is equal to TDS where T is equal to 4 sigma T cube. Okay, right. Here you have U which is sigma T power 4 and du will be 4 sigma T cube. Okay, and then you are going to substitute in this formula. Now you get ds is equal to 4 sigma T cube by T which is 4 sigma T square. So this is ds. You need to find the entropy. So I am going to integrate this ds is equal to 4 sigma T square dt. So S will be equal to 4 sigma T cube by 3. Okay. So on integrating, you integrate with respect to T. So you get 4 sigma T cube by 3. Okay. So this is the entropy for temperature T. Now you can see from here that S is proportional to T cube, right? So, when temperature T goes to 2T, then S will be proportional to 2T the whole cube. So, S will be proportional to 8T cube, right? So, basically, the entropy increases by a factor of 8, which is option C. An easy one. So, next is from December 2012. So, here, del W is the work done. Change in del W. Okay, change in work done is given as del W in a quasi-static reversible thermodynamic process. So, quasi-static basically means a very slow process. Okay, a very slow process which is coming towards an equilibrium position. Okay. Which of the following statement about del W is correct? So, how to find which of the following is correct? Now, del W is perfect differential if the process is isothermal. So, I have already discussed about isothermal process, adiabatic process and all. So, you'll have to, if it is isothermal, then you'll have to think what is the condition for isothermal and then substitute in your del W formula. You'll find if it is perfect differential or not. Next, del W is perfect differential if the process is adiabatic. That is the answer. I'll let you know. Third one is del W is always a perfect differential. No, del W is always not a perfect differential. That you have to remember. Okay. Because it is a non-state variable, hence del W will not be perfect differentiable always. Now, del W cannot be a perfect differential. So, cannot be a perfect differential is something different. So, we will see that C and D are not the correct answer. And for A, if you give the given conditions of isothermal process, and then you will find that del W will not be a perfect differential. Now for adiabatic, let us see how del W is a perfect differential. Okay, so here du is equal to dou Q minus dou W. Okay, so in an adiabatic process, dq will be equal to 0 and du will be equal to minus dw. Basically, dw is not a perfect differential, but du is a perfect differential. So basically, when du is perfect differential, then dw will also be a perfect differential. So hence option B is correct only when the process is adiabatic. Okay, so I hope you get this solution easily. The next is the ninth question, and here a free energy difference between the superconducting and normal states of a material is given. Just don't Don't get afraid of these words, superconducting, normal states, blah blah blah. Okay, you just have to find what is given in the question. There is some del f value, and psi is an order parameter, alpha beta are all constants, and we have to find the minimum value of del f. So basically minimum value of del f is very important over here, right? Minimum value basically means what? It is just kind of trying to tell you that you'll have to find the minimum of del f. So how do you find the minimum of del f? We'll have to differentiate del f, find the equilibrium points, and then substitute those equilibrium points in your del f value and find what is the minimum of del f. Okay, so the solution here is basically like we have written the del f as given in the question. So we'll have to find the minimum of del f. So you'll have to differentiate del f with respect to psi. So psi is one variable over here because alpha and beta are constant as given in the question. So on differentiating and equating it to the 0, you get your psi square to be minus alpha by beta. Okay, you can also write psi, but I have written psi square for our convenience in order to substitute in del f value. Okay, now we have got psi square is equal to minus alpha by beta, and now I have to find, okay, this is the equilibrium point. Now I have to substitute this equilibrium point in the original equation of del f, and I'll get the minimum del f value. So on doing that, I get minus alpha square by beta plus alpha square by 2 beta, which gives me minus alpha square by 2 beta, which is option B. A very simple question. So you'll have to just see what is asked. If you do not know what is asked in the question, then you can just, okay, leave that question and go further. But if you try to like remember what is asked, okay, minimum is nothing but this, then you can just use all these kind of steps and find the answer, but you'll have to first read the question till the end. Okay, so let us see the 10th question from CSIR December 2012, and here a quantity of gas is taken from state A to C. Okay, it is taken from state A to C by two paths directly, from A to C or from A to B to C. Okay, there are two ways. It can either go from A to C directly or from A to B to C. Okay, so now during the process of A to C, the work done of the gas is 100 joules and heat absorbed is 150 joules. And in the process A to B to C, the work done is given, we'll have to find the heat absorbed. Okay, so this is a very easy question. We just have to think from A to C, right? From A to C, we have dq and dw. We know du is equal to dq minus dw. So you'll have to think what formula connects these two quantities. So it is du is equal to dq minus dw. You can find du from here, which is 50 joules. And then now in this A to B to C, you'll have to find dq, right? You know du, you can use the same du because it is path independent. Internal energy is path independent. So for the entire system, if it goes from A to C or if it goes from A to B to C, it is going to cover the same path. Like it is going to cover the same area of the system. It is going to cover the same system. So the internal energy of that particular system will remain the same even if the path is changed. So we say that internal energy is path independent. Hence you can use the same internal energy for this A to B to C path. Okay, so now I'm going to use the same formula as here and I'm going to substitute for du and dw. So I get dq is equal to 80 joules, which is option B. So this is a very simple question. Just you have to think and remember the properties. That's all. So thank you. Like my videos, share my videos, subscribe my channel, and do not forget to hit the bell. Only when you hit the bell, you're going to get the notifications of my further upcoming videos, and you'll solve more questions from thermodynamics, and we are going to add up more important points. And at the end of the PYQs, I'll give you a revision session of thermodynamics so that it will be very much useful for you to learn the thermodynamics part for the exam. Okay, so see you tomorrow. Ta-da!